are heading to Cypress, California right now to head over to a satellite office of Race Winning Brands. Race Winning Brands is the parent company to a lot of companies you guys are probably familiar with, like JE Pistons, Wiseco, Boostline, Dart, Pack Valve Springs, a lot of others too. We're gonna go check out the new pistons and rods that are going into the engine that's now going into my Tahoe. We're also gonna go learn a little bit about what goes into designing custom pistons and rods for an application, because obviously this setup that we're using is not just off-the-shelf stuff. Let's get into it. Oh shit. Hold up, wait a minute. I just realized something. While we were editing this video, it kind of dawned upon me that many of you may not even know what the hell we're talking about in terms of what this Waylon build is, because it's been so long since you might have seen it. So let's do a real quick recap. Waylon was my 1997 two-door Tahoe that we did a Godzilla swap in with a big Garrett G47 turbo and a 4L85 from Gearstar as a four-wheel drive truck. And the original purpose of that truck was to do drag and drive events, to dominate on this versus that, and to just generally be a big street menace that would be a lot of fun and an overwhelming amount of power. Now that setup was all fine and dandy for what that purpose was, but directions changed a little bit. Now because we're doing Burnout Wars shows all over the country and it's a hell of a lot of fun, I decided that I cannot be on the sidelines, on the microphone, and not driving in the show. We're turning this truck into a absolutely savage burnout machine. And the way we're doing that is with a tried and true package from Texas Speed, featuring a Dart SHP Pro LS Next block, along with a Dart crank, some Texas Speed PRC heads, and right now we're going over to check out the rest of the rotating assembly from Boostline and JE. It's been custom made for this application, because we're going to be doing burnouts. It's going to be seeing a lot of heat, it's going to be seeing a lot of boost, it's going to be seeing a lot of violence, so everything has to be very, very dialed so that this thing can last season after season. Now the reason I've chosen to partner with these brands is very simple. Every single one of these products is all American made with American sourced material. And that's huge because we want this thing to last a long time. I hope this helps and catches you up. Let's get back to the episode. I had no idea this place was so close. Oh no, speed bumps. Oh, this car's worst nightmare is speed bumps. Okay. I don't know, there's other fast cars around here, so we'll just park here. Okay, we're here. Let's go check it out.
All right, the day's finally come. You get to check all this stuff out. After you, sir.
Thank you.
So this is it. We've talked about this stuff. You got to see all the design features, and this is the physical realization of everything that happened in SolidWorks. So It's a big deal.
All right. So these are the pistons and rods.
Pistons and rods and our total seal piston rings.
Okay. Should we go pistons first?
Let's do pistons first. Open that box up.
You ready?
There she is.
Oh, hell yeah, dude. You guys did the Burnout Wars logo and everything?
I mean, got to have the logo on there.
Oh, yeah. Oh, hell yeah. So we got the whole...
Yep. These pistons all went through our critical dimension process. So it's something we offer to the higher end race teams and a lot of guys who are really, have critical dimensions that they want to ensure that everything's manufactured 100% correctly. So it's good for us to go through and run everything through the lab. So all this is done on our CMM machine. So it's a coordinate measuring machine. Every piston, if you look on the bottom, is labeled. So this one is D. So if you go across the top here, that's actually this specific piston. Oh, so when you go through and look at all the measurements, so this will be all the measurements for that specific piston right there. So we check compression height, we check the skirt diameter, we check the ring lands, all the different critical measurements that will make your piston basically perform the best. That way when you get them, you know they're right, you can put the rings on, assemble them, and you're ready to rock and roll.
Hell yeah.
I did notice right here there was nothing that measured the girth index, since you're so concerned about that earlier, so we're going to have to add that to the next sheet.
Yeah, so the girth index is something that we're going to be bringing to all JE Pistons moving forward here. You're welcome, people. So the hard anodized looks awesome, by the way.
So what's neat about hard anodizing as opposed to like ceramic coating, you see pistons that are like gold ceramic coated. It's been popular for a few years now.
You guys have one of those over here? I could just kind of show what he's talking about?
Ultra piston. If we really want to get down to the difference, so this would be hard anodizing and this would be like our thermo coating.
Yeah.
So the difference between the two is this is a sprayed on coating, right?
Yeah.
Where anodizing actually grows off the part. So it's adhered to the part differently. So the easiest way to explain it is it's basically like sea monkeys that grow off the aluminum. So it's etching the part and creating that protection layer. So what's nice about it is people talk about coatings either flaking off or burning off. That will never happen with an anodized part.
Hell yeah.
So
this is like what we need for running methanol.
Nitromethane, if you ever want to step your game up a little bit. Nitrous.
Yeah, I'm on the nitrous.
All that kind of stuff.
Really?
Yep, just tip the can and make it happen.
Sweet, I like terrible ideas.
Yep. When making an anodized part, because everything grows, you'll notice on the spec sheet here, if we go down to the ringlands.
Yep.
So this piston tells you the ringland is, 0.0458. So it's 45.8 8/10 thousandths of an inch. So, but you have a 043 ring groove. So these pistons were measured before they went out, and the anodizing will grow the different amounts. So we have to make the ringlands bigger to accommodate for the growth of the anodizing. So now your ringland, there's another sheet on the back side there where it shows where the land measures 43 and 2/10. So that's something that has to be calculated into the part. Another thing that we do with a hard anodized part, if you can see, this is like the bare aluminum, right?
Yep.
So the advantage of having your top and second ring anodized is it prevents micro welding. So a lot of times when you have detonation or you like to run the rev limiter, because what can happen is you'll actually detonate the engine and it'll cause micro welding where the ringland tries to weld to the piston.
I see.
So that's one of the advantages of having a hard anodizing in the ringland, is it will prevent that from happening. So you get a longer life, you can do lots of stupid stuff and not have your ring stick in the piston and then everything locks up and shoots out the side. Okay. We're doing you a huge favor by making that happen right here.
I appreciate that.
So, but one of the things you have to realize is when you do hard anodizing, it basically forms an eggshell around the piston because it's a thin 2,000ths layer around the bare aluminum. So imagine you have an egg, you heat it up, you cool it down, the inside gets hot. So what happens is if you put a bunch of heat into the anodizing and it never comes out, you're gonna like heat cycle and put a lot of heat into the bare aluminum underneath the anodizing, and it can get softer over time faster. So traditionally hard anodizing isn't used on a street engine, but the way we can do that to fix it is by allowing the heat out. So our process here is the skirt diameter is actually dunk the whole piston into a tank, it's anodized, and then it comes back out and it gets machined, and from the third land or your oil land down, we machine the turn diameter or the cam and barrel shape that we talked about earlier. And so we actually machine the anodizing off the piston. So what that does is it gives it ability for the heat to escape the part so it can cool off. So the aluminum doesn't just heat soak in that shell of anodizing over time. So as the piston heats up and cools down, you can get heat out and you have oil that can run on there to also help cool the parts as well.
Nice. So that's something I had no idea about. Like I didn't realize that you create that pocket. So let's say if it doesn't have this.
Like a top fuel engine, right?
Yeah.
It lasts what, 5 seconds, 4 seconds, 3 seconds,
tear it down right after a run.
out it goes, right? So the thing about it is that it never goes under the heat cycle. You're gonna drive this thing around, you're gonna go do 5 minutes of burnout. It's gonna run in the engine at a couple hundred degrees, all these kind of things. So that's the biggest thing about a bare aluminum piston, is it has a specific duty life. Most people don't realize that. They think, oh, it's going to last forever. But aluminum can only heat up and cool down so many times before it fails, right? So all of our pistons, a forged piston is actually stronger than a billet piston because it starts off at a higher Rockwell.
Gotcha.
So over time, as a part anneals, the Rockwell gets lower and lower and lower on a part. So like we have a lot of guys who do circle track racing or drag racing that send their parts in for inspection, or they want to know, hey, is this part still good? You can Rockwell test a part, and after the Rockwell degrades so many points, you can say, you know what, I want to run that part again. The ringlands are going to be soft. It's going to put a hole in it real fast. So all those things are what you kind of learn over time to make things last long. There's a lot of little subtle details when it comes to making a custom piston to make it live as best as it can for your application.
These are multiple oil grooves?
So with that's a forced pin oiler. So you can see right here, this is the hole that's in the oil land. So as the piston comes up and down, so we'll just start from the top. So you have your top compression ring, which is In the AP steel ring here, it's a steel gas nitride top ring. It's 173 radial, so that's the thickness of the ring.
Okay.
So what that does is it provides more actual tension in the bore, so that you have a better seal under boost and stuff like that.
Gotcha.
So a ring, just like a piston, as it heats up over time, can lose its tension, and that's where you lose ring seal. You can see it has lateral gas ports in it, which also helps promote positive gas pressure behind the backside of the ring, which basically takes the ring and pushes it up against the cylinder wall to help it seal when the combustion process happens.
Gotcha.
This is the second land, which is extra thick to help support the top land under high boost. And then we have our power adder accumulator groove here, which helps relieve the gas pressure off the top ring, which is that little notch right there in the second land.
Just this little,
Yep.
It's hard because it's black, but just this little gap right here.
That's what she said.
Moving on.
So here we go. So then if we move down here, you can see then we got your oil land and all that kind of stuff. And then we talk about the cam and barrel shape, all that stuff that we talked about earlier. So back to the force pin oiling, there's an oil hole that intersects with the pin bore. So as the piston's moving up and down and the oil gets scraped off the cylinder wall, it forces oil into the wrist pin area so they don't gall. We call it either a banana groove or an accumulator groove around the two force pin oiling holes, and that's make sure that you have oil in the pin bore at all time.
Nice. So it just keeps it there,
Yep.
keeps it circulating.
Right.
Very cool.
So this is probably a piston for, I would say, one of our Ultra Series pistons for Honda or a Toyota small bore stuff. So you can see size does matter.
It's bigger and blacker.
Woo!
These are rad.
That's awesome. I think they're going to work great for you. So here, these are the wrist pins. We can talk about those too.
You know, doesn't it seem to get talked a lot?
Correct.
At least, you know, with idiots on the internet like myself. Do you mind if I
open that baby up?
Ooh, you got the. Okay.
So this is a DLC coated wrist pin. So it's like a diamond-like coating. They've developed it through NASCAR and Formula One over the years, and it prevents the pin bores from galling. Basically, the pin is the foundation between the rod and the piston, right?
Absolutely.
So most people don't look at it that way, but that's what's holding everything together. So you want to make sure you have the right material. This is a H13 pin, and you have one that's thick enough that'll support the amount of boost and pressure you're going to put to it.
Important things.
This is probably the strongest pin for your application.
We're gonna be running boost. So if you are too, H13, I guess, look that up.
Yep,
or
it's a
maybe,
good pin.
you know what, maybe I'll take a little break right now, and then I'll go into the science and try to do it really fast so we're not like getting out of hand. But if I can find it, hell yeah.
H13 tool steel is a versatile chromium molybdenum hot work steel that is widely used in hot work and cold work tooling applications. The hot hardness, hot strength of H13 resists thermal fatigue cracking, which occurs as a result of cyclic heating and cooling cycles in hot work tooling applications. Because of its excellent combination of high toughness and resistance to thermal fatigue cracking, also known as heat checking, H13 is used for more hot work tooling applications than any other tool steel.
Something I did notice is it's really like slick. Like
That's the coating.
feels-
So what happens is to do a DLC coated pin, it has to have a special surface finish. You put the coating over the pin. If there's any rough spots in it, it will actually show up in the coating. So these pins, we do them a little bit differently. Some companies just take a pin and then DLC coat it. What we do is we take a pin and it gets lapped down in a special polishing process so that the pin is actually 2/10 smaller than it's supposed to be, so when the coating's added, it's the correct 927 size.
You can't feel anything catching. Like on my fingernail here, it's like might as well be polished. It's cool.
Yeah, it's pretty cool.
We're going for longevity here.
Oh yeah, he's got to do 2 burnouts.
Exactly. Exactly. Well, you know, hey, we got 2 shows a day when we're doing it.
Yeah.
Okay? I would like to not be pulling this engine apart. That's why we're overbuilding everything, because it sucks to have to pull engines out and rebuild and put them back in. It gets expensive over time. So we want to do it right the first time.
You want to give it your best shot. Like we tell everybody, you want to engineer your parts to last. Weird stuff happens all the time. A fuel pump takes a crap, injector sticks. Like there's things that happen as you go along your build. I would tell somebody to like maybe sacrifice and wait on their build to spend a little bit more money to ensure that the longevity of the engine's going to last.
Because spend less money in the long run.
Correct. You know? It might be a little bit more money up front, but if you rebuild your motor 3 or 4 times, you've spent twice as much money as you would to begin with.
And time.
Yes, yes.
One last important thing. So forging everything here for JE.
Yes.
This is all American.
100% made in the USA, from the forging process down to everything. So
Okay. And then where are these being forged at?
They are actually made in Mentor, Ohio in our facility, so that's where they forge them. It's a USA-made aluminum bar that gets cut into a billet puck. It's forged there, and then it goes through the machining process. The coating's done there. Everything's done in-house.
Nice. So, American aluminum.
Yes.
American forged.
Yes.
American cut.
100%. Made in the USA.
What I'm talking about. We can guarantee that it's all made right. God damn it. All right. Let's get into these rods.
All right, Boostline connecting rods.
I'm excited about these.
All right.
So this is the V2 rod, right?
This is the brand new version of this rod. So take a gander at that thing right there.
There we go.
So if you notice when you open up the box, this is something that Boostline does that a lot of connecting rod companies don't. Just like your pistons, this is basically all the critical measurements of your connecting rod. Every rod goes through a 26-point CMM inspection, every single rod that we produce, so that when the engine builder or you, the person assembling the engine, gets it, they can go down each rod so that you can assure that the rod's made right, and when you put the motor together, you're not going to have any problems.
And if it's messed up, we know who did it. We know who to call.
Yeah. So this is the new V2 version of our Boostline connecting rod that we talked about earlier. So these rods are definitely, they're made right here in the USA. This is the first Boostline connecting rod that we've run through our plant in Mentor, Ohio. These aren't the first ones, but like the first series as we move down the line.
Nice.
So the rods have changed substantially in the design to increase their strength. So through all of our FEA analysis and our actual physical testing, the rods increased by 40% in strength.
Damn, nice. We're gonna get real technical with the nerdy stuff in a bit here. So if you're into that, you hang tight. But we're gonna go over like a brief overview here, and then we're gonna get really serious down to the nitty gritty in a second here. So 40% stronger than the first version.
The first version, yes. So we still use the same patented Boostline 3 pockets at the bottom, the design there, but the main differences come in the beam design and the area around the pocket. So what we did is change some of the thicknesses to make sure that they don't weigh any more than the previous version. So if you were building an engine and you had a set of Boostline rods and you're like, you know what, I've run these things for 3 or 4 years, maybe it's time to get a new set. They've lived a really good life. If you bought this brand new version, it would weigh the same as the previous version. You wouldn't have to rebalance your engine.
Oh, really? That's nice.
Yes.
That's nice.
We're thinking of you.
Let me ask you this. What kind of power are people able to put through something like this if it's well set up?
So the difference between power and RPM is the main debate on the connecting rod. So everybody wants to know a horsepower number, but you could have a diesel engine that makes 3,000 horsepower at 1,800 RPM, or you have a small block engine that makes 3,000 horsepower at 8,000 RPM. So the main thing that when it comes to equating the horsepower rating of a rod is the piston assembly weight. So if you have a piston assembly weight, which is rings, pins, locks, that weighs 600 grams, and you're going to turn it 8,000 RPM, the inertial load on the rod's going to be different than, say, your piston was 400 grams. It makes the rod will last longer, obviously, with a lighter assembly weight. So we did all the testing to make them stronger, and we tested assembly weights up to 780 grams to make, so it's like 200 grams more than a typical LS engine would be, right? Because if you had a 780 gram piston assembly weight, you probably couldn't balance the crank, put enough Mallory metal in it to fix it, right? So that's a balancing act, strength versus weight versus the ability to balance the whole internal rotating assembly. If you're gonna turn crazy amounts of RPM, put the best bolt you can in your rod. So this thing, you're probably gonna limit it to what, 7,500 RPM?
Yeah, like 12,000. Yeah.
Right. 7,500 RPM. Yeah, that makes sense. So with the way everything works and the beam strength of this rod, we redesigned everything to make sure that you could say, yes, it'll do 2,000 horsepower. So here's, if you're a good tuner, maybe a little bit more, because bad tune-ups kill still connecting rods. So if you detonate it or you overtime it, put extra pressure on the rod, you're going to blow stuff up no matter what you got. The tune-up is what makes everything live. So you got to have a good tune-up to make sure it lasts a long time. The thing about it is, as horsepower levels go up and cylinder pressures go up with boosted applications, a steel rod is probably maxed out in the 2,000 to 2,500 horsepower area, because after that you're getting so much cylinder pressure that the rod is pushing the oil film off the bearing. You don't have like a shock absorber like an aluminum rod where it will absorb that. So that's where, like, we tell everybody, if you're going to go above 2,000, maybe 2,300 horsepower, the aluminum rod's the way to go.
Gotcha.
It obviously doesn't last as long on the street or in a burnout because they just aren't designed for that, but that's kind of like the breaking point.
So we're doing a delicate balance between want the engine to live, we need it to do multiple things, which is, you know, big, sick burnouts, but be able to kind of drive it a little bit on the street if we want to, and then need it to last many, many moons.
And in making parts like connecting rods, pistons, like shelf stocking pistons, this is the inherent problem. Everybody wants an engine that does something for everything, right? So like you look at specialized racing like Pro Stock or Supercross or NASCAR or Formula One, everything is built for those specific applications. Like that's what that part was made for, that one engine. It's only going to do that one thing. Whereas all of these parts have to be able to work in every application, from a rock crawler to a burnout guy to a drifter, to drag racing, all these airboats, whatever you can think of, everybody's trying to put these parts together and make them live in every application. So from a manufacturing side, you have to have some like fail safes built in, like, okay, here's where we know it's gonna be work flawlessly at, and here's a point of no return. Do not ever go there, right?
Gotcha.
So, and it's just a little bit hard. Connecting rods are the hardest part when it comes to that type of manufacturing because there's so many variables.
Gotcha. So would it be safe to say that with this setup, in theory, 2,000 horsepower shouldn't be a problem?
Not a problem. I mean, we have guys that have tested this rod right now in LS and Hemi applications that have made 1,800 rear wheel horsepower with no problems.
Nice.
Which, when you think about it, is a lot more than 2,000 crank horsepower based on the reduction losses of the drivetrain and stuff like that.
Of course. Well, we're not going to be actually doing that. I mean, we just need it to be able to survive. It'll probably live at like 1,000, 1,200.
Why the you lying?
And that'll be.
You at least got to try once on the dyno. You
Yeah,
know?
you know, I mean, come on. Like, this is the internet. Of course, I'm going to try it, and hopefully I don't screw it up. But yeah, we're going to see how much.
Just get everything set up, and it should be no problem. You're going to run methanol and gas or E85?
No, it'd be methanol and E85.
Okay, yeah.
Hopefully we can do like a switchable system, but I think for the most part, I want to keep it safe, and it'll probably be on M1.
That makes everything live a lot longer in these things. It runs cooler. You know, you don't have as much heat in the engine, stuff like that.
Nice. What's going on, Michael? I'm Zach. Pleasure to meet you. So this is the rod.
Correct. Yeah, so this is the newly designed Boostline connecting rod. What we did is we changed some of the pocket geometry around, added some mass in certain areas of the rod around the big end and around the pin end to make it stronger. So what we did is we took the old Boostline rod, and if you compare it to this Boostline rod in the FEA analysis, this current design is 40% stronger.
Nice.
That's just from, you know, the rod's been out for a few years now, and we've been able to learn from, you know, customer feedback, from our own testing on how to improve the rod and make it stronger. And the goal is, with any product here at, you know, JE or Boostline, anywhere in race winning brands, is to make a better product and keep evolving it as we go. Some of the areas we did was we changed the geometry up around the pin end. When the combustion cycle happens in an engine and it fires, there's a shock wave as you're trying to compress the air and fuel, and it goes up and the spark plug fires. There's a shock wave that goes down the connecting rod. And what that does is that's taking all the load and sending it down the beam of a rod. So what we've tried to do is take the design and transfer the load. So say you're going to squish the rod together in a vise. You're going to see where there's a load that happens, and obviously there's going to be points of failure as the load gets stronger and it tries to compress more. So by transferring the load down and around the beam, what it does is it takes it from a pinpoint area across the flat here, and transfers it and equalizes the load to the outside edge of the beam. And then as it transfers down the beam, there's a pocket that's a secondary pocket that's cut right here in the rod. You can see right there. The 3-pocket design is recessed into the rod, and what that's doing is it's allowing the load to transfer around the big end better. So on the high boost, high cylinder pressure rods, when you take a motor apart that's run on the rev limiter a lot or gone down the drag strip a bunch, you're going to see a thumbprint on the bearing.
Yeah.
And that's usually from the cylinder pressure pushing on the rod.
Ah.
And everybody thinks the bearing's wearing, but it's because you're losing oil film because there's so much cylinder pressure pushing the connecting rod down up against the oil film on the rod bearings.
So the name of the game is dispersing that pressure so we can get even oil flow through the bearing.
So you're trying to transfer the load, that shockwave that goes down the beam, and you transfer the load around the big end. And what that does is it equalizes the load on the beam, makes the bearings last a lot longer. And that's something you just learn over time in testing. You know, we've done everything we can to engineer a higher horsepower rod that is the same weight as the original rod. As we gain horsepower levels, wrist pins get thicker, pistons get thicker, and that creates more and more reciprocating weight in the engine, and the whole piston mass is what creates a connecting rod failure, because you know, you get a piston and rod assembly that weighs 750 grams, turning 8,000 RPM with 50 pounds of boost on it is just a recipe for disaster on all areas.
Is this actually recessed in slightly in there?
Yeah, it's recessed into the rod, and it has a really, if you can zoom in a little bit more, we've changed the radiuses around. So the radiuses in these pockets that are machined are bigger radiuses, which create a stronger pocket, reduces cracking and stress on the rod. What you're looking at here is some of the FEA analysis that we have done. So the connecting rod in the FEA analysis is based off of cylinder pressure. That's what we're looking at the data. So what we're trying to do is we shoot for a target, a max pressure that we're after, and that's basically the yield strength of the connecting rod material. So what we're trying to come up with is, okay, we have our 4340 material, we know what the yield strength is, we know what the failure points are, and then we can go and back through the simulation based on cylinder pressure. So you can see there's different stresses that go along here. So what we're trying to do is go through and look at the internal stresses, the combustion pressure stresses, so basically the loading and unloading of the rod. So you can see as the wave goes down the rod here, you can see how the pressure is dispersed around the big end, down here and down the side of the beam. You don't see any real hot spots or anything like that. Yeah. So this connecting rod would be where, let's say it's pulling the rod apart, right? When like you're decelerating or you're just hauling ass and you're like, I'm gonna just do a power shift from third to second gear. That's what you're gonna see on the stress right there. So you can see there's more stress on the pin end because it's trying to rip the piston off the top of the rod. And you'll see more stress around the bolts because that's typically what fails. So the heat mapping, you can see the stresses on the rod and how everything is designed to make the bearing live its longest. And we do our best to engineer it as strong as possible, but the monkey behind the wheel can just change everything we designed all of a sudden and kaboom, it's done.
I have been said monkey behind the wheel.
We try to do our best to provide the best product through engineering, dyno testing, all the above, but there's still going to be some type of failure that you can't predict or happen, you know? Things just happen. So if we can build in a little safety into the rod, it just helps everybody in the long run have a better part that's not going to fail. So the new design has been flawless. We've had really good testing, and that's why we've moved it into production. And so we'll be switching everything over within the next 3 months as we go through the production process and our old inventory moves out and we change the design. It's just going to be a running change through production.
Nice.
So you can see the evolution of the bolt design as well. So it seems like a small detail, but changing how much surface area is on the rod where the rod's clamped together obviously affects its strength as well. The more surface area you have around the rod, the clamp load will hold better and stuff like that. So there's just small, minute changes that you go through in the evolution process that really makes a good product. That'll probably give you the biggest overview from revision 1 to revision 2 where you can see the difference in the rods.
The first things I notice are this ridge here. I don't know what you would call this, but this like seems
bigger radius.
Okay, it's a little bit girthier there. I do notice this arc here, whereas opposed to this has like kind of a flat.
Another area that you can see here is on the corner of the rod, right next to the 3-pocket design. You can see the difference in material thickness.
Oh yeah. Is this another like little ridge here that's been extended?
That's where I was talking about the pocket being recessed.
Oh,
so the main reason for that was we didn't lose any strength by doing that, but we were able to match the weight of this rod. Because as you start adding a little bit of weight here and there and everywhere, trying to match the weight so it wasn't excessively heavy was one of the main goals in the redesign of the rod.
There seems to be more contoured here rather than...
A little bit more connecting rod clearance for bigger camshafts. That way that they're the lobe, you know, as it moves around in the engine, your cam lobes right there. We're trying to give you as much clearance as possible if you're going to run the big thumpers or whatever they call them these days.
You got to run that HAWG in there.
That's true. The side profile, there's really not a lot of changes because it's based on widths, offset on the big end, stuff like that.
Gotcha.
So an LS rod typically runs on center, so there's not a lot of changes. The main changes are down here in the cap design. You can see there's a little bit more pronounced on the cap design on the way it's machined, and that's to give some increased strength to the way the cap load is so that it's stronger in the corners because there's a little bit more surface area, so it makes the cap and big end stronger as it tries to pull apart.
Nice. I feel very confident that this motor's not going to come apart.
Hopefully you can make that dream come true.
I'm going to be better. Yeah, we're trying to do everything right here. This is the piston?
This is your piston right here.
Oh, nice.
In digital space, good old SolidWorks. As you can look at the piston, obviously, you can tell it's for an LS just by looking at it.
Yep.
You've probably blown up enough to see what they
you know,
look like.
I've actually not blown up an LS. I'm pretty
Man,
good
you're
with...
a rare company. I'm impressed.
Plenty of my friends have done it, though.
Yeah.
It does sound like Oh yeah, that's Rod.
When we're designing a piston for the high horsepower level and the intended use, obviously you're going to beat the crap out of this piston, right? It's going to be on the rev limiter, smoking the tires, you know, hanging your hand out the window, high-fiving all the bros at the sausage party. So here you can see... Wow.
He knows. You've done this before.
Well, I know how it is, you know. Everybody thinks they're doing it for the chicks, but it's all about the sausage party, you know.
If you want to get chicks, don't get in the cars.
It's just how it is. I've been to SEMA. I see who lines up for the autographs. I know what's up.
Anyway, Pistons.
So some of the key features you want to look at, obviously the overall design, but what we do is we have some engineering standards that we go through based on horsepower and boost levels. So here at the top of the piston, basically they're going to look at the dish volume. So basically that's for the intended compression ratio that you're after, your bore, your stroke, how far the piston's in the hole, and the chamber volume of your cylinder head. So most people don't realize when the piston comes up, the valve is actually in the pocket. So that's when you're talking about piston to valve clearance, right?
Yeah.
So at top dead center, you know, everybody thinks it's at top dead center, but it's not. It's before top dead center. It's where the lift is on the valve, and it's typically the valve is actually stuck in the pocket. So then the question comes, how does the air get out of the pocket if the valve's in it, right?
Yep.
So by doing big radiuses and making little swoops around the pocket, because as it fires, it's trying to pull air and fuel into the center of the combustion chamber. So you're trying to get as much air out when the valve is in the pocket. So by doing some radiuses around the pocket and around the corners there, you end up getting a little bit more cross flow when the piston's up and the valve's in it. So it actually makes it a little bit more efficient when it fills the combustion chamber.
Nice.
So there's some neat little tricks like that. You can see we have contact reduction grooves, lateral gas ports, we have a power adder accumulator groove. Everybody thinks back in the day they used to take the top ring and move it way, way, way down in a real thin second land. Well, under high boost pressure, you have all the gases pushing down on the top ring. Another thing is, like, here's your edge of your piston, but your ring is probably out over here somewhere. It's outboard in all of the combustion pressure. So if you're firing a bunch of PSI onto the edge of the top or the top of the ring, it's pushing down on the second ring, which would cause second ring failures because the land pinches a second ring. Most turbocharged and supercharged applications, they'll pinch a second ring because there's so much pressure pushing down on the land. So that's why we go through, and obviously you need to have the top ring down far enough out of the combustion temperature so that it doesn't just get hot and try to micro weld itself to the ring land. But so you can look at the stack of the lands, we can see the second land is almost as thick as the top land, and that's what's going to create a really, really strong part.
Ah, okay.
So
let me ask you about this. This area up here, is that relieved so that pressure can kind of dissipate in towards the piston and just kind of give it more surface area?
Well, we call it contact reduction grooves. Some people call them anti-detonation grooves. So the way they work is you have fuel going into your cylinder, right?
Yep.
Basically, you have a big ring around the top of your piston, which is the crevice from the edge of this to the edge of this cylinder bore, right?
Yep.
So as fuel enters into the combustion chamber and into the cylinder, there's always excess unburned fuel that's not atomized, right?
Oh, yeah.
Because fuel weighs twice as much as air, so as you turn it around corners, around short turns, around valve seats, all that kind of stuff, as the air speeds up, the fuel weighs so much it separates out of the airstream because it weighs more.
Yeah.
So this particular part of the piston helps re-atomize unburnt fuel in the combustion process.
Nice.
Because there's little areas on there, so it kind of breaks up a fuel droplet and helps atomize it into the combustion process.
Oh, cool. Kind of like creating turbulence a little
Yes,
bit.
that's the whole idea of it, is to
Okay.
create a little turbulence to help reintroduce unatomized fuel into the combustion
Sweet.
process.
All right. Party on.
It's been around for a long time, but that's really the most effective way that it works. You can see there's a lot of strength engineered into this piston for pin flex, which is you have these struts coming off the pin towers, and you have a strut that connects other struts running in line into the skirt. So what causes a piston to failure under really high boost pressure is, a lot of people will call it oil canning, but it's actually pin flex. So 10 years ago, everybody ran a really thin wrist pin because they wanted it super, super light. It was going to rev up fast. Nowadays, thicker is better. As you said before, it's all about the girth, right? So
Gotta get that girth certificate.
that's a good one. I like that. So the thicker the wrist pin prevents the piston from flexing. So at high RPM and high boost, the piston pin actually will flex up and down like this, right? And when the pin flexes, it hooks in the piston, obviously, right through here, through the connecting rod, and it'll actually cause these towers to flex. That's why there's bracing across the towers, to prevent the towers from flexing in and out. Because when that flexes in and out, it'll crack right through the top of your valve pockets on the piston, because that's what's working so hard, is the towers flexing in and out will stress the dome of the piston. So obviously this is a very thick piston all the way around. So you can see, I think it's 260 thousandths thick here. You got a really wide area of pin engagement. That's going to help strengthen the part. So imagine so much pressure that this thing flexes up and down on the edges, right? And then it'll cause a crack to run through the top of the piston. So obviously a thick wrist pin helps that. So like this area right here, from here to here, I don't know, we call that the bottom of the dish to the machined underside of the piston, is 260 thousandths thick, which will obviously make a lot stronger part. So that's based on your application, right? So some of our engineering standards, I would say, on, I don't know, 1,500 horsepower engine, we try to leave things 220 thousandths thick. So here you're at 260, so you got the extra beef. So
Nice.
we want to make sure that nothing's going to fail. So, and then it gives you a better cross section. You can see just how thick all the lands are to create that strength. It just gives you a good cross section. You can see just how thick the part actually is. Because if people ask us all the time, how thick should they make the lands, or how thick should the deck of the piston be? And it's all based on the application and intended use. That's why it's a custom piston, right?
Exactly.
So our shelf pistons work really, really good, but if you're going to like the most compression, the most horsepower, you're going to just set the world on fire. It's kind of hard to do that with a shelf part or something you buy off of eBay, right?
Yeah, understandable. It's cut into there.
Well, that's,
Right,
if you
like for
flip it
the
upside down,
upside down, like the
it's
little
part of
hole.
the forging.
Yeah.
So that's actually just the machining, because we did a cross section. They machine the outboard pocket, so this has, the whole deck is uniformed. So instead of like having a thin part that's 100 thousandths thick and a thick part that's 200 thousandths thick, they can adjust the part on our forging.
Yep.
They can move it up and down, and then when they machine it, they can say, okay, we're going to come here and underhead mill this stuff, and we're going to set the depth. So, okay, this is going to be 260 thousandths thick in every area of the part. Because we're underhead milling it, we can control it based off of the forging.
Gotcha.
So if we didn't do that, there'd be areas of the forging that might be a little bit thicker, might be a little bit thinner, but this way we can make sure that it has the same thickness in the deck all the way throughout the part,
Awesome.
which makes it stronger.
Science.
If you look at the skirt profile, I'm sure your particular pistons have some of our new cam and barrel designs on the skirt. Everybody thinks it's a piston being round, but it's not. It's more clover-leafed, right? That's the shape of the part. So, you know, obviously we have our skirt shape, and then we have a cam shape which goes around the part. So one of the problems with LS stroker motors is when you have a 4-inch stroke, 4/100 stroke, 4 1/8 stroke, as the piston travels down through the cylinder, there's like the sleeve length, how long the cylinder is. The more the piston sticks out the bottom of the bore, the more it rocks. We've, over the last few years, done a lot of testing and developed a lot of new shapes of the skirts, which is the transition from just underneath the oil land to the bottom of the skirt, which we'll call that shape right there. So In the past, years ago, when there weren't big strokers and the piston never came out of the bore, there was tapered skirt designs that were really stable, but the farther the bottom of the skirt sticks out the bottom of the bore and you have a taper, then it creates more rock.
Yeah.
Because of the taper angle on the skirt. So if we move our transition point up to, we'll say 60, 80, 100 thousandths underneath the oil land, so the piston is riding, we'll say, across this area here, that is a part that never sticks out of the bore, right?
Yeah.
So at the bottom of you're going to have as much stability at the bottom as you will at the top. So our new shapes, this shape that's particular on this part, I would imagine, probably would rock at 6 thousandths piston to wall at the top, maybe 26 thousandths if we were to rock the piston from top to bottom in the bore. And when it's all the way at the bottom, it might grow another 5 thousandths. A lot of people measure it. You take this piston, run it all the way up to the top of the bore, put your dial indicator on it, push on it one side, and it goes up and down. So it would, from bottom to top, total travel would be 26 thousandths.
Yes.
So in the past with a taper skirt, if you took that all the way down to the bottom of the cylinder where it's sticking out the bottom, you would have maybe 60 thousandths or 70 thousandths rock. Which, think about it, if your piston goes to the bottom and it rocks around, your rings aren't designed to rock up and down. They're designed to move in and out of the grooves. So then it creates excess ring wear, bad seal, all that kind of stuff because it's hard to overcome. So if we take this all the way to the bottom now, instead of having a transition down here, we have a transition on our skirt that's up here. It maybe will rock 35 thousandths instead of 70 thousandths.
Can we turn it? Can I kind of see how that works? Like
it's hard to tell in the 3D drawing because it doesn't show the taper angles or anything like that, but it's just a point of reference.
I got you.
So if we made the piston completely round, like this, and we have excess material here, when you heat up a part, when you heat the piston up, it expands based off of these strut towers, right? So if you were to take a piston and heat it up to 200 degrees and you started measuring places that expand more than others, this particular forging, because of the way the struts are, you're going to see it expand right off the bottom of the strut. So it'll grow outward instead of completely around first because of the thickness of material.
Gotcha.
So when the shape's cut into the part, you'll see where it will dip in. It's hard to, you can't see it on here, but it's in our lathe programming. The shape of the skirt will dip in around the strut, come in here, dip around the tower, so that it gives added clearance to the part as it grows.
Oh. Whoa.
That's when people are talking about a cam and barrel shape. So you have the skirt taper, and then you have the shape around the part, which creates that clover leaf I was telling you about, to pull in. So we were just going to do a line so it would be stick out farther here than it does here, like that, so that as these parts grow outward, it allows more clearance. I mean, we're talking, 2 or 3 thousandths. You would measure it with a blade mic by hand, or you could run it through a CMM. But those little fine details are what make the piston expand uniformly, so that you don't stick a skirt when you first fire it up, or you just pull it off the trailer and you're going to be a hero on your way to the burnout box and show everybody how badass you are with the cold rev. This will prevent you from locking the skirts up as the piston expands, because an aluminum piston will expand faster than a block when it gets temperature in it. So those are all little fine details that go into the part to make it live a long time, perform its best. And the whole goal is to have the piston rock as little as possible. So you want to run as tight as clearance as you can to have the best ring seal. But there's areas where you have to sacrifice piston to wall clearance, or certain areas like that will prevent from the most maximum ring seal, but that's where gas ports come in and all these other little areas that help aid in the gas pressure behind the ring, which create a more positive seal. So there's a lot of little things that go into a piston that people don't realize. They just think it's, an aluminum slug.
Yeah.
So there's a lot of fine details and years of experience at JE to, do the testing, all the stuff it takes to come with these little fine details to make the best part possible.
Hell yeah. Well, my brain's about to explode. So I hope yours is too, and I hope you learned something. We're going to put lots of detail on the screen so you can see what the hell we're talking about in here. But I appreciate you walking us through all
not
this.
a problem, man.